G'day guys, welcome to lecture 3 of topic 2, inclined planes. Here are your learning intention and success criteria. Please complete the KS table. Pause the video while you complete this. Okay, now hopefully looking through here you saw a few things. One of these would be what is a free body diagram. We need to know what that is in order to be able to use this tool. And finally we need to know what is an inclined plane. If we don't know what an inclined plane even means, then how can we do any of the math about it? Secondly, in terms of skills, well, we need to be able to do this skill, determine the force of gravity due to mass. We need to be able to represent forces for a free body diagram, so you need to know those forces. And finally, we need to be able to solve them. So let's do a little bit of revision, because we've done forces before, but we're going to use this as our starting point. I'd like you to consider a book sitting on a table. Let's draw our table. There's my table, and here's my book. Now, what forces are there? I'd like you to pause the video and I want you to draw this and label what you can on your picture. There's the Earth. So label the forces. Now, hopefully you identified that there is gravity on this book. So there is the force of gravity between the Earth on the book. And remember that the force of gravity pairs with gravity. So this force of gravity pairs with the force of gravity of the book on the Earth, and we can see the objects pair up, the type of force pairs up, so that's our force pair. There is certainly a force of gravity between the table and the Earth, and the table and the book, but they're so small we don't care about that at the moment. Now, the second force I hope you put in would be the normal force. And you may have stated, or you may have represented it somehow, that it is equal and opposite to the gravitational force here. Now I do want you to recognize that this normal force does not pair with the gravitational force. We can certainly see that it is acting on this object and it is balanced, so therefore it is not moving, but the normal force pairs with the normal force of the book onto the table. Okay, we can think of that as a contact force of the book onto the table, and here we would have a contact force of the table onto the book, and that is what is creating our normal force here. Realistically I should draw these the same size as these other two arrows, but I don't want to make it too messy. So remember that gravity always pairs with gravity, and normal force pairs with normal force, or in this case contact forces are what's creating it. Now, a couple of other forces we've looked at are friction and tension. So let's make our scenario here where we have our book, but it is attached to a string, and from that string is hanging a mass. Now this mass has a force due to gravity of Earth on the... what's what I'm looking for? Earth on the mass. Sorry, I forgot my symbols there for a second. And so that force of gravity here is transmitted through this rope, through this string, to become a tension force. This object is pulling on our book here on the table. It's also true though that this book is pulling on here. Now what it's pulling with will depend entirely on what is happening with this book. If it's sliding, then pull will be a little bit less. If it's not moving, then its pull will be equal. But there will be some pull, otherwise the rope won't really do anything, it'll just slide straight off. So if this book isn't moving, and we've said that it's stationary, then what is it that what is acting against this? And remember, we know that friction, the friction force, okay, and here it is acting against the net movement. So friction force doesn't exist to start off with. We've got our gravity and our normal force, so that balances off that first movement, and then tension comes along and starts to pull. There is a net movement happening. Friction then goes, I'll join in guys, and acts against the net movement. If instead of us having some tension here, we had someone pushing from this side, friction would go, oh, I'm going to jump to the other side, just to make sure that I'm always joining on the weaker side. It's kind of nice like that, but it is a little bit slippery. It just appears out of nowhere at the very end. Okay, so we've got our four forces, and these are ones that we should be labeling whenever we do our free body diagrams. So what is an inclined plane? I'm going to draw an inclined plane here. Pen. And an inclined plane is any surface that is resting at some angle. Like it could be a ramp, it could be a driveway. It's just something that is not parallel to the ground. And I'm going to put my book back on top. Now let's draw the forces. Obviously, we know that the force of gravity is acting down, but then the second force we drew was the normal force, and we know that the normal force acts perpendicular to the surface. I'm just going to do this in a different colour so that we can see it a bit clearer, but that means my normal force is up here. And here, these two are no longer perpendicular to each other. Before, in the previous one, they were. Before, we could see that the normal force was perpendicular to the gravitational force, and so they opposed. But here, the normal force is not perpendicular to the gravitational force. We would write this as the force normal is not, we use exclamation marks generally to say is not, parallel to the gravitational force. So that's a bit of a problem. We'll get back to that in a minute though. Now, if we consider what happens if we keep lifting this ramp up, eventually this book is going to slide down. So that tells us there has to be something acting down, some pulling force acting down the ramp. So we have a little bit of a problem here. We know the force of gravity, we know how to work that out, we know that that just equals mass times the gravitational acceleration, but what's the force due to the normal force, and what is the force that is pulling these objects down? Obviously, if this is not moving, there would be a friction force that would oppose it, but until we know what that is, we're not going to be able to figure out what that is. And if we don't know what that is, well, then we don't know how to balance it against this gravitational force. So one of the strengths of the vector system that we've been talking about is that you can make your x and y be any orientation. And what I mean by that is we're very used to doing x and y up and down, left to right. But we don't have to. We can orientate our x and y in any direction we want. So the question then becomes, what if we orientated our x and y like this? There's our y, and there's our x. And what's really interesting about this is by doing this, we get our normal force is now just straight up y, our pulling force here is just straight down x, and our force of gravity becomes something that is pointing off at an angle away from my y-axis. So we've only got one vector here that we need to really think about, because if my gravitational force is pointing off in this quadrant, then some of it is acting down, which would oppose the normal force, so that would be creating the normal force, and some of it is acting down the plane, which would then explain why we have a pulling force. So these two forces here are linked to gravitational. We just need to work that gravitational force out. Now, instead of calling this x and y, because we find that a bit more annoying, we generally let x and y be these normal orientation, we're going to call this one parallel, and that's the symbol for parallel. We're going to call this one perpendicular, and that's the symbol for perpendicular. Okay, so we can use this to figure out, well, what's this gravity going to be in this new orientation? So I'm going to draw what's called a general solution here. I'm going to go through the proof of how to work out that little angle there that we didn't know, and from that we will be able to work out a general rule that we can then use. So I'm going to draw my force of gravity, but instead of drawing it from the center, I'm going to draw from the base to make something a bit obvious for us to see. So we want to know, well, how much of this force of gravity is acting down, perpendicular, and how much is acting horizontal, parallel. So we have Fg Fg perpendicular, my apologies, Fg perpendicular, and over here we have FG parallel. Because we're trying to break this larger vector into two smaller pieces, and I know that these have to be at right angles to each other, I know that these will be the smaller parts of the triangle. Sometimes it's a common mistake, people will draw all the way down to here, and then they will end up with a bigger triangle. You can't have that. That has to be the maximum force. This will be less, and this will be less. So, we have to work out what is this angle here. I'm going to call that alpha. I'm also going to label this angle in here. I'm going to call it the Greek symbol phi. We know that this must be right angles because our gravitational force must be perpendicular to the Earth's surface. We've learnt about that. But what's also useful is that this corner here is also perpendicular because we've defined that this is a perpendicular angle. So from this we can now write two sums. Remember, the angles of a triangle add to 180. So that tells us that this angle plus this angle in the corner here must equal 90 degrees, because this one down here is also 90. And you know, this plus this equals 180. Take away 90, these two here equal 90. So let's write that. Plus phi equals 90. But we've also by definition said that these two must equal 90 because this is perpendicular to the surface. So phi plus alpha equals 90. And because they both equal the same thing, then our symbols here must equal each other as well. Plus phi equals phi plus alpha. And we can see here we've got a phi on both sides. And so theta equals alpha. And that's fantastic. We know now that this here is just going to be the angle of our inclined plane. These are what we would call similar triangles. So now we can work out our general rules. We've got a right angle triangle. That means we're going to use some basic trigonometry. We're going to use our cosine and sine to break it down. We're going to resolve our vectors like we've been doing before. So cosine of theta equals adjacent. We see adjacent here is this side. So that's FG perpendicular divided by FG. And sine of theta will then have to equal FG parallel. Okay, this bit over here, opposite it. Sorry, I've drawn that symbol wrong there. That should have been FG parallel over FG. If we rearrange that, we get our two rules. And I'm just going to draw our two rules up here because we're going to use these rules. We don't need to reprove them all the time. FG parallel equals FG sine theta, and FG perpendicular equals FG cosine of theta. Good news, bad news. Good news is these will work for any inclined plane situation. Bad news is they will not be provided to you in your workbook because it's just the use of using vector decomposition in order to figure out, or vector resolution, in order to figure out what these are. I would recommend that you memorize them before an exam so that you have them there, okay, in case you need to do any work with inclined planes. For your student experiment, you're not going to need to memorize them because it's an experiment. But when we get to our end of year final exam, you may want to consider memorizing them the night before an exam. So let's have a look at some examples. These are all in your textbook, and I'd recommend that you pop that open while I go through these. So, worked example 2.3a, so this is chapter 2.3. A 15 kilogram bag of fertilizer is allowed to slide freely down a smooth, frictionless 30-degree incline. So if the question doesn't tell you that it's frictionless, just assume that it is. If it doesn't tell you that there is friction, then it's frictionless. Okay, so make the math easy for yourself. We want to find two things, net force and acceleration. So I'm going to draw our situation. We have a 30 degrees and we have a 15 kilogram bag, 15 kilogram. We want to know the net force down the incline. So we want to know, well, what's the force pulling it down here? Because we need to think about net force, there's that word net, we need to go, well, are there any forces acting up the plane? And we're told that it is frictionless, so friction force equals 0. This one coming down, as we just established on our general solution, is our parallel component, and we have a formula for that. So I'm going to just jump straight to the formula. FG parallel equals Fg sine theta. Now, Fg is just the force of gravity, which is mass times acceleration. So that's 15 times 9.8 times the sine of 30. We've got a nice nifty little sum there. Let's plug it in. 15 times 9.8 times sine of 30 gives us 73.5 newtons. Second question asks, what is the acceleration? Well, we know the relationship between mass and acceleration. This we could also say is equal to the net force because, or the net force parallel because, that's the only force going down the parallel. Acceleration, though, is equal to net force divided by mass. Remember, we do need the net for that. So that's equal to 73.5 divided by 15, which equals 4.9 meters per second. And you might be going, you multiplied by 15 here, but then you just divided by 15. Why did we have to do that in the first place? I mean, why do we have to bother finding the force if we could have just done 9.8 times sine 30 and got the acceleration? And the short of it is that in some simple situations like this, you can, unless you're asked to find the net force. Does it really matter if you find force then acceleration, or you just jump straight to acceleration? We only found force really because we had to. But the problem is some situations will be more complicated and you won't necessarily be able to ignore your mass so easily. You can at times, but you have to know how to, and knowing how to do that is really tricky. So it's always better, and I would recommend this heavily as just a basic safety procedure. Work in forces, and then if you need an acceleration, go back to it. Okay? Never ever work in accelerations, always work in forces. Let's have a look at example 2. A 34 kilogram child sits on a slippery slide that has an angle of elevation of 40 degrees to the horizontal. If the friction force is 110 newtons, determine the motion of the child. So what does this word motion mean? This word motion is asking about acceleration, because it's either acceleration or velocity, and since we know nothing about this situation apart from what the force is, the only thing we can work out about its motion is its acceleration. So again, let's draw a basic plane. The angle is 40 degrees. The mass sitting on it is 34 kilograms. Okay. We know that there is a friction force. Okay. And we know that there will be a force due to gravity in the parallel component. So we need to know the motion. We want the acceleration. And to get the acceleration, we need the net force. To get the net force, we're going to have to add some forces together here. So we're going to need this, and then we can add it to this. So, and the reason I know that friction is acting up that way is because something's going to be pulling it down. That's the only thing that's acting on it, and so therefore friction will act in the opposite direction. So let's work out the gravitational force. Fg parallel equals Fg sine theta equals 34 times 9.8 times the sine of 40, and we will end up with some answer. 34 times 9.8 times sine of 40 gives us 214 newtons. Now the sum of forces is going to equal Fg parallel plus friction force. We have to give one of these a positive and negative. I generally say down the plane is positive just because that's what happens. I put an object on a plane or on a ramp, and either it goes down the ramp or it doesn't move. I've never put something on a ramp and had it spontaneously go up the ramp. So we just let down be the positive, down the ramp be the positive, because it makes sense to us. Friction force in this case will end up being negative. So that means that's going to be 214 plus negative 110. It wouldn't matter which you did, but as long as you understand and interpret your question. And so that gives us a force of 104 newtons. But the question is after motion. We need to now work out what that is. Acceleration equals change of F divided by m equals 104, sorry, not change, sum of F. 104 divided by 34. 104 divided by 34 gives us 3.06 equals 3.06 meters per second squared. Okay, Now, in this case, we sort of see now why we need to use forces, because we won't always have things that can be easily turned into accelerations. So example C and example D use a little bit more complexity. So the first two are what we call a free situation. There's an object, it's sitting on a ramp, and it's going to move or it's not going to move. This one now involves a bit of tension, so let's have a look. We've got a 525 kilogram coal truck being pulled up a 25-degree incline by a cable. The cart moves up the track at constant speed. Calculate the tension. This verb here, constant speed, is really important. Constant speed means change in velocity equals 0, because it's constant. That's what constant means. If the change in velocity is 0, that means the acceleration equals 0. And if the acceleration equals 0, that means the net force must equal 0. So that's a really important thing to recognize, because we're going to need that information. Let's draw our inclined plane. This is at 25 degrees, and we have our mass of 525 kilograms, and we have a tension, some sort of force pulling it up. Force, tension. But it's an object on an inclined plane. There must be a force of gravity pulling it back down. Now we're told it's constant speed. That tells us that the sum of forces must equal 0. So let's write down that. The sum of forces must equal 0. To calculate that, we have Fg perpendicular plus force tension. Okay? Well, that means we can work out the tension of the cable. We just need to work out that, because now, if I take this, Fg theta parallel will equal negative Ft. They are opposite, but they'll be the same magnitude because they're balanced. We have an equation for that. Fg sine theta, negative Ft. Mass is 525 times 9.8 times sine of 25, and that's going to equal negative Ft. 525 times 9.8 times the sine of 25 is equal to 2,174 newtons equals negative Ft, or tension equals 2,174 newtons up the hill, because that's the direction tension is going. Negatives and positives can be a bit tricky to deal with when you're doing inclined planes, and so I generally like to give my answer in a contextual sense, in terms of saying, well, my direction is up the hill, rather than saying my direction is negative or my direction is positive, or whatever answer you end up giving. So just be careful with that. So let's have a look at example D. There is an example E that I'm leaving for you to have a poke at, but if you can do this, follow along with this one, you'll be able to do that fine. We've got a 525 kilogram cart. It's getting pulled up a 25-degree incline, but it's getting pulled by a hanging mass of 300 kilograms to apply the force. Again, determine the motion of the cart. So there's that word again. Determine the motion. Okay? And so we need to work out the acceleration in this case, because we can't work out velocity. Let's draw our system. We have an inclined plane, 25 degrees, mass of 525 kilograms, and there is a rope going to another mass equals 300. So if we just look at the cart here, we have the force of gravity of this thing pulling it down, and we have the tension force here pulling it up. And the tension force is equal to this force of gravity by, we'll say M. Apologies. So, well, what's FGM? Let's work that out. FGM of this bugger here is mass times gravity, 300 times 9.8. 2940, and we've got Fg parallel, so let's work that out. Fg parallel equals Fg sine theta equals 525 times 9.8 times the sine of 25. 525 times 9.8 times the sine of 25 is, oops, 525 times 9.8 times the sine, could help if I hit that button, equals 2174 newtons. So let's work out the sum of forces on this axis. The sum of forces is going to equal my force of gravity plus my force of tension. And so that's going to equal 2174 plus, well, let's go negative 2940. 2174, take away 2940, gives us negative 766 newtons, or 766 newtons uphill. So now we want the motion. Well, that should be easy. We take our force, we divide by mass, we get acceleration, because we know that acceleration equals sum of forces divided by mass. The problem is the mass is not 525. This thing here, this cart, is not moving on its own. This is a whole system connected. If this is accelerating at some value, this must be accelerating at some value. Because while it's true that this is getting pulled up by this tension force, this force here is pulling this up. So this is some force of gravity here is being opposed by the tension force there. But this tension comes from this force down here. In fact, we could use that to work out the acceleration of the whole system if we wanted to as well, because we would be able to work out the net forces on this thing, and then that would equal for the whole system, and again we would get the same number. So we can't use 525 for the mass. We have to use 825 the mass, because it's the mass of the whole system, and that's why this is a fairly tricky question, at least to begin with. 825 kilograms divided by 825. And so that gives our acceleration, will equal, and I should probably put that as negative actually, is going to equal negative 0.93 meters per second squared, or 0.93 meters per second squared uphill. Okay, so this thing is not going to accelerate. If I do 776 divided by 525, it's not going to have an acceleration of 1.46. It's going to have an acceleration of 0.93, because if this thing was moving independently, that means that would be moving at that same speed because it's connected, and this thing is pulling that, but that would be faster than the force of gravity on it, so that's a problem. Okay, so you've got to consider the whole mass of the system. On this question here, there wasn't some mass pulling it, it was just a machine winding up the rope. That's why it was a constant pull, because the tension was constant. But on this one, it's not some machine just pulling it up, it's an actual object falling, and the whole system must be considered. Okay, so that's a tricky part. So in this video we've learnt the following. We have used mass and acceleration due to gravity to calculate the force of gravity. We've drawn some free body diagrams and labelled forces, and we've calculated using a free situation and a tension situation for inclined planes. So the free was example A and B, and the tension was example C and D. For your entry to class, please access the audio book and download chapter 2.3 from your Check Your Learning PDF, and I want you to complete, remember this is the unit 3 for text. Copy your answers into the 2.3 space on eLearn, so those are questions 2 to 6 from chapter 2.3. I would suggest looking over chapter 2.1 and 2.2, but we only did this content just a short while ago back in lesson 1.7, and so I'm not going to ask you to do those questions, but it would be a good resource if you're finding vector resolution challenging, or you need a quick refresh on type of forces. So just have a look at the start of chapter 2 there. Thanks for listening, guys. Have a good evening.